Welcome. We're delighted to have you here, and I am particularly excited about our speakers in this track, and I promise you, you're going to learn a lot. So without further ado, I'd like to invite Chris, and many of you know Chris as a wonderful researcher and contributor to our journal. And I'm got to read this little bio, Chris, and then you burst up on the stage like a movie star. No, you can stand right there. Okay. Okay. No. So you stay right there. Yep. So, where are we here? Chris Masterjohn, PhD, is Assistant Professor of Health and Nutrition Sciences at Brooklyn College in Brooklyn, New York. In 2012, he obtained his PhD in Nutritional Sciences from the University of Connecticut, where he studied the role of vitamin E and other antioxidants in regulating the metabolism of methylglyoxal, a potentially toxic byproduct of energy metabolism that appears to contribute to diabetes and cardiovascular disease. From the fall of 2012 through the summer of 2014, he worked as a postdoctoral research associate at the University of Illinois in Urbana, where he studied the interactions of fat-soluble vitamins A, D, and K. And there he worked with our beloved Fred Kumerow, who is now 101 years old. Just a wonderful man. Chris created and maintains a website, cholesterolandhealth.com, which is home to his blog, The Daily Lipid. He has published 8 peer-reviewed scientific papers and has contributed regularly to the pages of Wise Traditions since 2004. So please join me in welcoming Chris Masterjohn.
All right. Who's ready to talk about saturated fat? All right. So I'd like to mention a few things before I jump right into the material. One is that I've given a lot of talks about fat in the past, and usually they've focused on why saturated fat's not bad for you. And today the talk is going to focus more on the positive things that saturated fats do within the body. And so what that also means is that I'm not going to purposefully be putting up any material critiquing ideas of why saturated fat is bad for you. However, I am leaving a big chunk of time at the end for questions, so if you want to hear, if you have specific concerns about those sorts of topics, I think it's fair game to talk about that in the Q&A period. Now, the second thing is understanding the essential roles that saturated fats play in the body has historically really been the domain of molecular biologists and other basic science people instead of nutrition scientists. And that's because of historically how our thoughts about nutrition have tended to develop. So if you look at early nutrition science, especially over the course of the first half of the 20th century, when we really got most of our understanding about the essential nutrients, everything was geared towards trying to understand what happens when you deprive a laboratory animal of a nutrient and you can define a specific deficiency syndrome that comes when you don't have that in the diet. And from before the 20th century, we knew that you can synthesize fat from carbohydrate. We can do it, any other animal can do it. And among those fats, we synthesize saturated fats and we synthesize monounsaturated fats. And it wasn't until 1929 that anyone made a convincing case that certain fats were essential in the diet. And those fats, which we call the essential fatty acids, are the polyunsaturated fats, not the saturated or monounsaturated fats. Now, probably part of the reason why we get a specific deficiency syndrome if we have 0 polyunsaturated fats in the diet, which is extremely difficult to do in a human but can be done in a laboratory animal, is because the need for those fats is relatively small compared to our need for saturated and monounsaturated fats for structural purposes. And therefore, we have evolved the ability to synthesize saturated and monounsaturated fats because we need them so much that it's very dangerous to not be able to have them. But no one was really asking the question, does it matter to support optimal health to have saturated fats or monounsaturated fats in the diet? And by the time nutrition scientists really started getting into the question of how do we support optimal health and how do we prevent chronic disease, that was already the time where people were saying saturated fats raise cholesterol. The key to minimizing heart disease is to eliminate saturated fats from the diet. So saturated fats never really had the chance for anyone to ask the question, is there some minimum intake of saturated fats that we need in order to support the optimal functioning of the body? So what I'm going to show you today in terms of the essential structural roles of saturated fats in the body is primarily going to be coming from our understanding of how cells work and how saturated fats play essential roles in cellular biology. I'm going to shift gears then and talk about some of the importance of certain specific saturated fatty acids in energy metabolism. And when I get into the latter part of the presentation, I'd like you to keep in mind that that's probably going to make more of a difference in terms of what we're consuming in the diet than the essential structural roles, simply because only a small portion of what we consume in the diet is actually needed to make our tissues, and most of what we consume in our diet is needed to obtain the energy needed to repair that structure, to maintain that structure, and to prevent it from falling apart. And that's because if you've taken chemistry or physics, or you've seen some cartoons about entropy, you may be familiar with the second law of thermodynamics, that in the absence of a deliberate input of energy to maintain something in an ordered state, everything tends toward disorder. And so we as humans tend to eat our body weight in food several times a month. And the main reason we need so much food is because it requires so much energy to constantly maintain, repair, and support the order that we've created. With those caveats, let's get into the material. All right. Before we talk about what do saturated fats do, let's first talk about what they are and where we find them. So all fatty acids are primarily hydrocarbons, and you can see stearic acid depicted here, which is a saturated fatty acid. And you can see it's essentially a long string of carbon atoms, and each carbon atom has all its extra binding sites filled with hydrogen. Except for the two carbons on the end, all of the carbons are bound on one side to another carbon, on the other side to another carbon, and each carbon has 4 binding sites, and they're all filled with hydrogen. So the reason that we call it saturated is because all of the possible binding sites for hydrogen are saturated. In unsaturated, such as oleic acid here, which is predominant in olive oil, or linoleic acid here, which is predominant in many vegetable oils, there are at least 2 sites where the hydrogens are missing. And you can see one such site here, and you can see in linoleic acid, which is polyunsaturated, that there are 2 such sites. When that happens, the carbons form a double bond, and when they form a double bond, they develop a kink in the molecule that takes away from their straight shape. As I'll talk about later in the presentation, the carbon between 2 double bonded carbons, so that would be this one here, is also very vulnerable to a process called oxidation that can damage the fats, and only polyunsaturated fats have these carbons situated between 2 double bonded carbons, and therefore they're uniquely vulnerable to oxidation. But I'll talk more about that at the end of the presentation. This picture here shows you a little bit more clearly how the molecules, or how the atoms in the molecule take up space. So we have on the right hand in each panel a structural formula that emphasizes the carbon skeleton. And then on the left we have a space-filling model, and each bubble represents an atom, and this just shows you a realistic depiction of the proportion of space that the atoms take up. And you can see in a monounsaturated fat, it has a clear kink whereas in a saturated fat, it's very straight. That makes saturated fats very packable, and it makes monounsaturated or polyunsaturated fats a little bit shorter in total length because they're bent, and a little bit harder to pack together. And so for that reason, if you have fats that are very saturated, for example, butter tends to be solid even at room temperature. If you take something like olive oil, which is intermediate, it's mostly monounsaturated, it'll be liquid at room temperature, but it can get pretty hard in the refrigerator pretty fast. If you take something like corn oil, which is mostly polyunsaturated, it tends to stay very liquid and very pourable even if it's cold. So where do we find these fats in nature? Well, I think one of the misconceptions that many people have is that saturated fat is primarily associated with animal fat. And in fact, the least saturated fats and the most saturated fats are actually plant fats. And most animal fats occupy some space in between. So you can see by far and away the most saturated fat that is available on the commercial market in the U.S. is coconut oil. Its close cousin palm kernel oil is very similar. After that we have cocoa butter, and then only then do we get into the animal fats, such as butter, beef tallow, then we have palm oil, another plant fat, then we have lard, and so on and so forth, until we get down to the marine oils, such as salmon oil, which has 20% saturated fat, and then we get the seed oils, which have the least saturated fat, or even olive oil. But any of these oils all contain some saturated fat, so even olive oil is 14% saturated fat, and that reflects the fact that all living beings, even plants and even the fruits that they bear, require saturated fat for essential purposes. But I think it's very much a misconception that we should associate saturated fats specifically with animal fat, not only because of how they're distributed in the foods, but also because of how traditional diets are distributed. So I've put here several diets in detail from 3 different Pacific islands where the predominant fat is coconut, but the amount of coconut in the diet, and therefore the total amount of fat versus carbohydrate in the diet, is very different between the islands. And then I've compared them as a reference point to the Inuit, who have the lowest plant consumption in the world probably, and the highest consumption of animal products. And of course, these are marine oils that they're primarily consuming, but this does demonstrate the point about whether saturated fats should be associated with plants or animals. And then finally, I've put in the Americans here. So if you take in the Pacific Islands an island like Catawba, you can see that they consume about 70% of their calories as carbohydrate and only about 20% of their calories as fat. That's not the highest carb, lowest fat traditional diet that exists, but I think it's pretty fair to say that within the spectrum of traditional diets, that's a pretty low fat, high carbohydrate diet. But you can see that because their fat comes from coconut, even on this very low fat diet, and compared to Americans who, historically it varies, but we tend to consume 30 to 40% of our calories as fat, they're consuming 17% of their total calories as saturated fat, which is about 50% more than what Americans consume on a diet that's much higher in fat. Americans are consuming about 11% of their calories as saturated fat on average. Now, if you take the opposite of extreme, we have in the Pacific island of Tokelau, a diet that's very, very similar to that on Catawba, only they eat a lot more coconut and they eat a lot less carbohydrate from starch. And you can see that their saturated fat intake is about 50% of their total calories. That's about almost 5 times more than what Americans are consuming. The Inuit consume saturated fat intakes that are very similar to what Americans are consuming, with a large proportion of animal food intake. Now, of course, we could take other traditional diets that where instead of marine oils, land animals are predominating, and would find saturated fat intakes that are higher than in the Americans or in the Inuit. but they'd also be lower than the coconut-rich diets of the Pacific Islands. So, I would say from this, first of all, that saturated fats versus polyunsaturated fats versus monounsaturated fats has very little to do with whether the diet is rich in animal products or plant products. Instead, I think what we could say is that across the spectrum of traditional diets, those diets have gotten most of their energy either from carbohydrate or from traditional fats that were low in polyunsaturated fatty acids. Not absent, but relatively low in polyunsaturated fatty acids, so that the predominant fat calories were being supplied by monounsaturated fatty acids and saturated fatty acids. So if you look at traditional foods and oils outside of coconut, you have traditional fats like butter, tallow, lard. All of those are low in polyunsaturated fats and contain a balanced mix of monounsaturated fats and saturated fats. Or even if you take something like olive oil, traditional in the Mediterranean, it has some saturated fat, but it's mostly monounsaturated fat, and it has relatively little polyunsaturated fat in it. I would also note that all three of these islands have some level of evidence that heart disease, even in people who are old enough to get heart disease in our society, is essentially absent on those islands. And that's despite the fact of having not only the highest intakes of saturated fat in the world, but in the case of Tokelau, consuming 4 to 5 times as much saturated fat as Americans, which makes it unlikely in my eyes that saturated fats are the primary thing contributing to the incidence of heart disease in America. All right, so now let's move into the material on what are the essential roles of saturated fats in the body. Well, I showed you before that if you have a double bond in a molecule, it creates a bent structure that makes it hard to pack together. If we look at our cellular membranes, this has a very important impact on the nature of the cellular membrane. In cell membranes, whether it's on the outside of the cell or wrapping all of the internal organelles within the cell, you have a phospholipid bilayer. And these phospholipids are part phosphate, which is indicated by these large red bubbles, and they're part fatty acids. The phosphate is water-soluble, the fatty acids are fat-soluble. So if you have the blood and the extracellular fluid on the outside of the cell, that's primarily water-based, and the water-soluble phosphate heads are facing the water. And on the inside of the cell, you primarily have a water-based fluid, and again, the water-soluble part of the phospholipids is facing them. And then within the interior of the membrane, you have a fat-soluble interior that prevents things from easily passing through the membrane unless you have specific ways of controlling it. And so this is very important because if we want to have a cellular environment where we're optimizing to have a specific function, we need to have some boundary that controls what comes in and what goes out. And that's true, of course, even of this room. If we didn't have doors in the room and people guiding people in here and out here, it would be quite a mess in here. We're very much controlling what's going on in here. Cells need to do the same thing. But the composition of these phospholipids is critical because the cellular membrane has to have a certain consistency to it. What this picture on the left is showing you is that these phospholipids are mobile. They tend to easily diffuse laterally, they tend to easily rotate, and on great occasion they may flip from one layer to the other. But overall, they're moving around in a fluid manner so that the cellular membrane has roughly the consistency of olive oil. If the cellular membrane were to be mostly unsaturated fatty acids depicted on the left panel on the right figure, or if it were mostly saturated fatty acids depicted on the right, it would have very different characteristics. You can imagine from what we said here that if it's unsaturated, these could move around too much. If it's saturated, they could pack together too tightly. And in addition to that, you can also see because all the unsaturated fatty acids are bent, they're shorter. And if the membrane is enriched in saturated fatty acids, it's actually going to be a different thickness. So what the cell does with this then is try to achieve a specific balance of saturated and unsaturated fatty acids. And the typical phospholipid looks like the one that's shown here. This is the same thing, just shown to you in 3 different ways. You could look at any of them and see the same thing. I'd look at the one on the right because it's a little bit simpler than the 2 on the left. And what you can see here is that the typical phospholipid has 1 saturated fat and 1 unsaturated fat. That means that the typical cellular membrane is about 50% saturated fatty acids, 50% unsaturated fatty acids. But there are also specific components in the membrane where saturated fats are enriched. And here I'm showing you a concept called a lipid raft. And the idea here is that the cell sometimes needs to anchor specific proteins in specific places so that they can interact with one another. For example, in this raft area here, these proteins here might have important interactions with each other, or there may be a protein here that's a receptor for something outside the cell that needs to be transmitted to a specific location inside the cell, and there's a need to stabilize those proteins together. And so in the lipid rafts, what you have is areas where there's a lot more saturated fat and cholesterol, and that helps do 2 things. One is to stiffen the membrane so these proteins can effectively stay together. And the other thing is to thicken the membrane so that some proteins are allowed in and some proteins are allowed out. So if you imagine the relatively more unsaturated portion of the membrane, everything's diffusing more easily. This protein here could diffuse more easily, but you can see this protein has a portion that goes through the cellular membrane that's too short to cross the membrane in the thicker area dominated by saturated fatty acids. So if this membrane doesn't belong in the lipid raft, the fact that the lipid raft is enriched in saturated fatty acids will prevent it from getting into the area that it's not supposed to be. In addition to these structural roles, there are also specific saturated fatty acids that are used to anchor proteins in membranes. And for the most part, we've known those to be myristic acid or myristate and palmitic acid or palmitate. And just this year, we have new evidence that stearic acid plays a similar role. So I'm showing you here an example of using myristic acid as an anchor for a protein. If you imagine this protein, which looks like someone oddly made it to look like a peace sign to me. In any case, if you imagine this protein needs to be anchored to the membrane, here you have a molecule of myristic acid or myristate, which is a 14-carbon saturated fatty acid, and that constitutes the anchor that traps the protein here. Sometimes this could act as a switch to activate or deactivate the protein because there may be signals that can cause that anchor to get tucked inside of the protein, which would disable it from binding to the membrane or allow it to come out and actually anchor to the membrane. This process is called myristoylation. There's an analogous process that uses palmitate. Palmitate is a 6-carbon saturated fatty acid. It's named for its abundance in palm oil, but it's very widely distributed. Most foods, even vegetable oils, to the extent that they contain saturated fat, contain a rich abundance of palmitate because throughout plants and animals, it's the most abundant fatty acid that's synthesized. And in this case, you do something very similar, but this time it's called palmitoylation. And it's very similar to myristoylation, except that the bonds are very easily reversible. And so it's thought to play a major role in trafficking proteins between different areas in the cell and localizing those proteins to particular membranes. It wasn't until this year that we had evidence that stearate does the same thing. And in this case, the data that I'm about to show you on this slide are interesting because although this experiment was done in fruit flies and human cells, it provides a small hint that certain neurological diseases could increase our dietary requirement for saturated fats. So what they did here is, first, they took Drosophila, which is the fruit fly that's typically used for genetic experiments, and they deleted the gene that codes for the enzyme that makes stearic acid. And they said, okay, what happens to those fruit flies? And what happens to the fruit flies is that their mitochondria fall apart. And that's because mitochondria in their normal metabolism, remember the mitochondrion is the powerhouse of the cell where most of your ATP is made for energy. They tend to adopt their specific shapes by constantly fusing together or breaking apart. And there's a specific protein that gets stearoylated with stearic acid that's essential for mitochondria to fuse together. And if you don't have that protein joined to stearic acid, you lose the ability to fuse mitochondria, and mitochondria instead are constantly breaking apart. They showed that the same thing is true in human cells, and then they said, wait a second, let's see if this is dietarily important. And what they did was that they took the gene that's believed to contribute to Parkinson's disease in humans, and they put it into the flies, so that the flies would get something very similar to Parkinson's, only Parkinson's in a fruit fly kind of way. So you can see that it hurts their longevity. They don't survive as long. It hurts their ability to do normal fruit fly things because their nerves are degenerating. You can take the flies apart and see the evidence of abnormalities in the mitochondria and energy metabolism, in nervous system regulation, and so on and so forth. And so here they said, okay, we're going to let you make your own stearic acid. We're not going to play around with that. We're just going to give you Parkinson's disease. And what happened was, if you look at the data on the left, when the flies were given the gene for Parkinson's disease, here is a measurement of the degree of mitochondrial fragmentation. The Parkinson's disease caused a very large increase in the degree to which mitochondria were fragmenting or breaking apart. And then they said, okay, what happens if we add stearic acid to the diet? Stearic acid is C18 here. And so you can see on the right, they added stearic acid to the diet, and that mitochondrial fragmentation was brought completely back to normal. And that could indicate that in the case of Parkinson's and perhaps other neurological disorders where you have a defect in mitochondrial energy metabolism or structural defects in the mitochondria, maybe in those cases you need more stearic acid in the diet to help restore that disease state to normal health. On the right, you can see the survival of the flies. And you can, I was going to say the ones that had Parkinson's were dropping like flies, but that doesn't work here. Okay, anyway, so they were all dropping like flies, and you can see even the control ones. But the ones that had Parkinson's, as shown in the solid dotted, or the dark dotted line here, they were really, really dropping like flies. And if they supplied stearic acid in the diet, it brought it back up to here. So you can see the survival of the flies was very close to normal. Not quite, but compared to the untreated flies, the flies that got stearic acid their survival was almost brought back to normal. Okay, now this is in flies. Does that apply to humans? Well, I would say there's a big difference between flies and humans. And I pity the scientist who's trying to get the ethical board to say, I want to treat Parkinson's with a diet high in saturated fat. Probably not going to happen simply because of our biases right now. But hopefully eventually this is something that we could actually study and say, what if you do increase the amount of stearic acid in the diet? Can you actually see improvement in humans? And maybe if there's additional work in animals that would substantiate the plausibility of that, maybe we can convince ethical boards and convince scientists that this is something actually worth looking at. But this is kind of the problem that I referred to when I opened my talk, which is that it's fine for molecular biologists and cellular biologists to say, what is the structure of those cellular membrane? What do these fatty acids do? Because they're just looking at the way things work. And once you get into how does that translate to what we should eat, that's where all the politics comes in. That's where all the public health concerns come in. And there's a lot more timidity, I think, in that research in looking at questions of whether saturated fat in the diet is valuable. And so we have a lot less research in that area. Okay, so it's important to remember that humans synthesize stearate and all of these other fatty acids endogenously. And of course, we can get all these saturated fatty acids from the oils that we've referred to before, particularly animal fats and tropical oils would provide this stearate. So that raises the question of, is there any limit to our ability to synthesize saturated fats? And or is it taxing in any way to synthesize saturated fats such that it would be valuable to provide those fats in the form of animal fats and tropical oils in order to spare our need to make those fats? So toward that end, I'd like to show you some data on fatty acid synthesis, otherwise known as de novo lipogenesis, or DNL, which means to make new fat. And that means mainly we're making it out of carbohydrate. There are some amino acids from which we can make fat, but overwhelmingly when we make new fat, we're making it from carbohydrate. And in humans who are in energy balance, de novo lipogenesis is considered a very minor pathway because we don't actually make that much fat. So if you look at men on a standard Western diet, men tend to synthesize 1 to 2 grams a day of fat from carbohydrate. That is probably 175 to 150 times less fat than what those men are eating in their diets. With women, it's very similar, only it changes during the menstrual cycle, such that there's an approximately 3-fold increase in de novo lipogenesis during the follicular phase. But again, that 3-fold increase is a 3-fold increase from 1 to 2 grams per day, and so the total amount of fat that a woman is producing even in the follicular phase from carbohydrate is very small compared to the amount of fat that she's eating in the diet. There are a variety of conditions such as obesity, diabetes, infection, and inflammatory disease that also increase this amount to 3 to 6 grams per day. But again, even in obese people, the amount of fat that they're synthesizing from carbohydrate is negligible compared to the fat that they're taking in the diet. Then the question becomes, what would happen if you put someone on a diet where most of the calories are coming from carbohydrate and they're not getting that supply of 1 to 200 grams of fat per day? And to my knowledge, the only such study that I know of put people on a 70% carbohydrate, 15% fat diet. It's relatively similar to the Katavan diet that I showed you earlier, only it's a little bit lower in fat. And that increased fatty acid synthesis to about 10 grams per day. Even 10 grams per day is pretty low. One thing that I think would be valuable to know is what happens to someone who doesn't have any fat in the diet. Does it increase even further then? And I don't think we know the answer to that. But these data would suggest one or both of two things. One would be that our need for these fats is pretty small, therefore we don't synthesize these fats. The second would be, or a variation of that would be, actually maybe the need is somewhere around 50 to 100 grams per day, but even people who are eating 15% of their calories as fat are getting pretty close to that, so they don't have to make much more. Or the other possibility would be that there's something taxing about the need to make fat from carbohydrate that makes our body not really do it just because it would be good to have those fats around, but only when it really, really needs to. So I'd like to explore both of those possibilities. The data I'm showing you now suggests that there really is no limit to the amount of fat that humans can make from carbohydrate. This is a study that was called the response to massive carbohydrate overfeeding in man. And what they did was they first took everyone and put them on a low carbohydrate diet and had them exercise. When you fast or you eat a low carbohydrate diet that primarily depletes your glycogen stores in your liver. Remember, glycogen is the primary storage form of carbohydrate. When you exercise, you primarily deplete the glycogen stores of the muscles that you're exercising. So in this run-in to the study, if the men exercised and went on a very low carbohydrate diet, that could maximally deplete their glycogen stores. And that allowed these investigators to say, okay, what's the maximum amount of glycogen you can store? And what is the exact point at which you start turning extra carbohydrate into fat? Then they put them on a diet that was 86% carbohydrate by calories, but was also way beyond their caloric needs. Right? So this isn't just high carbohydrate. They're eating too much total calories compared to what they need for energy, and most of it is coming from carbohydrate. To put that in another way, their total carbohydrate consumption alone exceeds their total requirement for energy. The other 14% of their diet is even further beyond their caloric requirements. So in the run-in period, you can see they weren't doing anything with carbohydrate because they didn't have a supply of it. But then they show you three things. In the shaded area, they show you carbohydrate oxidation. That means burning carbohydrate for energy. In the white area, you see glycogen storage. That means turning carbohydrate into glycogen to store as carbohydrate. And then in the speckled white area, that's net de novo lipogenesis. That means synthesis of synthesis of fat from carbohydrate. So what you see is that the first thing that happens is they get almost all of their energy requirement from carbohydrate when they're on this diet. Whatever fat is in the diet, they're probably storing that in their fat tissue. If they have some requirement for 2,000 calories a day, let's pretend, that's about 500 grams of carbohydrate. They're basically burning through 100% carbohydrate. And then the extra carbohydrate beyond their caloric needs is first stored as glycogen. But you can see it only takes about 3 or 4 days to completely saturate the ability to store glycogen. That's because glycogen takes up a branched structure that takes up a lot of space and absorbs a lot of water. So when we store carbohydrate, it's voluminous, it's heavy, and it's wet. And when we store fat, it's light, it's easily stackable, packs tightly together, and it's dry. Okay, so if we were to store, right now, if take a typical person with healthy body composition who isn't overweight, that person probably has 30 times as much fat as glycogen. And if that person were storing all of that energy in their fat as glycogen, they'd look like a water balloon because it would take up so much space and it would all be absorbing water. And there would be no way you could move efficiently because you'd be wobbling around like this at best. So this ability to store glycogen is extremely limited. And as soon as you start to get about a quarter full, you start turning some of the excess carbohydrate to fat. But then after it fills up, net de novo lipogenesis takes over. And so with no end in sight, you just keep making fat from the extra carbohydrate. And at the end of the 10th day, they took them off the high carbohydrate hypercaloric diet, so net de novo lipogenesis stopped. But this indicates to me that the body has virtually unlimited ability to convert carbohydrate to fat. Now that doesn't mean that that doesn't mean that it's desirable to synthesize fat from carbohydrate. And that's because doing so actually taxes our energy supply and steals energy that's desperately needed for a lot of other important things. So if you're a fan of technical jargon, NADPH stands for nicotine adenine dinucleotide phosphate with a hydrogen on it. But basically what this does, NADPH, this is a form of niacin or vitamin B3 that carries high energy electrons that are taken from glucose to other molecules in need of those high energy electrons. And if we're going to engage in de novo lipogenesis, we need to use lots of NADPH, and that means that we're sapping the supply of NADPH that is used for other things. Some of those other things include antioxidant defense. Every time we neutralize a free radical or a molecule of hydrogen peroxide or a lipid peroxide in our cellular membranes, all these forms of oxidative damage that occur in our cells, those electrons always can be traced back to electrons that were taken from glucose using NADPH. So if we're going to engage in a lot of de novo lipogenesis, we're taxing our antioxidant defense system. NADPH is also used to recycle vitamin K. Every time we use a molecule of vitamin K to activate a protein, it gets used up and it's got to be recycled again. Only with that recycling can we use a molecule over and over again thousands of times and actually get adequate vitamin K from our diet. If we didn't have that ability to recycle vitamin K, all of us would have to be taking that 45 milligram dose of MK4 that they give to the Japanese to prevent osteoporosis. That's thousands of times higher than what we get from food. And none of us would have been able to survive when no one was synthesizing vitamin K. Okay? So in order to recycle vitamin K, we need to use energy from NADPH. And the same thing is true of folate, which I'll be talking about in a different talk on methylation tomorrow. So it hasn't been studied in a way that I could confirm and say with certainty that when we're synthesizing fat from carbohydrate, we are indeed impairing our ability to defend ourselves against oxidants and to recycle our vitamins. But again, this question hasn't been studied in enough detail. So I think you could plausibly hypothesize and suggest that the body's self-limiting its ability to synthesize fat from carbohydrate except when it really needs to, because these other processes are so critical that they take priority during most of the time. But in the absence of any evidence clearly defining what the minimum saturated fat intake is, I think it would be hard to say whether it's more than what these people are getting. But again, they're getting the fat in their diet plus what they synthesize. And so perhaps the minimum amount of fat is somewhere around 30 or 40 or 50 grams for these structural purposes. Perhaps it's somewhere around 10 grams for these structural purposes. It's not really clear. But in any case, I do think it's probably valuable to get the fat that we need for those structural purposes through actually eating the fat rather than synthesizing it from carbohydrate for the reasons described here. Now, as I said in the beginning of the talk when I was leading into this, our requirement for food, our quantitative requirement for food, the reason we eat our body weight in food a couple times a month is not because of the turnover of these molecules in the cell membrane that we need to literally replace them all of the time. It's because we require so much energy in order to support those structures by constantly maintaining them and repairing them. So then, let us turn away now from the structural roles of saturated fats and look at some of their roles in energy metabolism. and in other non-essential functions in the body. Okay, so first of all, coconut oil is rich in the 12-carbon saturated fat lauric acid. About 45% of coconut oil is lauric acid, and triglycerides containing laurate can be digested to monolaurin. And monolaurin has activity against a wide variety of bacteria, fungi, and viruses, including Candida albicans, Staphylococcus, Heliobacter pylori, influenza, Epstein-Barr, measles, and HIV. Not saying that eating coconut oil is going to cure all of these conditions, but given that monolaurin is effective against all of these things, it makes sense that during times where your priority would be immune support, consuming your fat as coconut oil is probably going to be very beneficial. Now, lauric acid is often considered a medium-chain fat, but lauric acid is metabolized for energy very similarly to the long-chain fats. If you look at coconut oil, about 15% of the other fatty acids in coconut oil are capric and caprylic acids, which are 10 and 8 carbon fatty acids. And these fatty acids, although they're saturated, they have specific metabolic effects that's primarily a result of the fact that they're small. Because these molecules are small, they very easily fit through cellular membranes to get into the mitochondria, for example, and they're much more easily burnt for energy than other molecules. Typically, when we eat a mixed diet, the carbohydrate in the diet stimulates insulin, and insulin makes us burn carbohydrate instead of burning fat. So insulin stimulates burning carbohydrate for fuel and inhibits burning fat for fuel. But the mechanism by which insulin inhibits burning fat for fuel is to shut down a transport system called the carnitine shuttle that allows longer chain fats to get into the mitochondria where they can be burned for energy. Carnitine is often sold as a supplement. Carnitine can be obtained from meat. We can synthesize carnitine ourselves, but it requires a lot of nutrients. You may be familiar with it through any of those means. When carnitine is sold as a supplement, the reason people take it is for this reason, because it helps shuttle fatty acids into the mitochondrion and helps improve your energy metabolism. But because the 8 and 10 carbon fatty acids can be burnt for energy without using the carnitine shuttle, that means that if you eat a mixed meal that contains coconut oil, 15% of the coconut oil fatty acids will not, their metabolism for energy will not be shut down by the carbohydrate that's in that meal. Okay, so if you put, what do people like to put on bread besides butter? Okay, yeah. My grandmother said in the Depression, all she ate was Wonder Bread with lard and sugar on it. Okay. But maybe on your sourdough bread, you can put lard without the sugar. Okay. So if you put lard on your piece of bread and you eat a full meal's worth of calories like that, the bread is going to take preference for your energy metabolism and it's going to stop you from metabolizing the lard. But if you put coconut oil on the bread, then 15% of those coconut oil fatty acids can be easily burnt for energy at the same time as the carbohydrate in the bread, which suggests that your total energy expenditure could be higher. And to some degree, this is also true of butter, because about 5% of the butter fatty acids are also small like these fatty acids and have similar properties. But coconut oil will be more effective because 15% of those fatty acids have these characteristics. This has primarily been studied in the context of MCT oil. That stands for medium chain triglyceride oil, and you can buy that as a supplement. MCT oil is produced from coconut oil by isolating all of the 8 and 10 carbon fatty acids. So MCT oil in the market is 100% capric and caprylic acids, and that implies that the data I'm about to show you are probably true for coconut oil, but the effect is probably about 6 times smaller for coconut oil. So in order for studies to see that effect, it'd have to be 6 times longer and probably be bigger as well. Okay, here's one of the first studies that was done on this topic. And they said, if you compare MCT oil to beef tallow, and remember MCT oil is 100% 8 and 10 carbon fatty acids, beef tallow, like most other fats, is 0%. How does that affect your fat oxidation? So they took 17 healthy obese women, randomized them to receive the same diets but in 2 different orders. And this was done for 27 days, and all the women underwent both trials, separated by 4 to 8 weeks. The data on the left are from the first day, the data on the right are from the day 27. And so what you see here in the left is the acute effect, and what you see on the right is the I don't know if you could say that's long-term, but it's relatively long-term effect compared to day 1. And what you can see is that in the line on the top, this represents the MCT oil. The line on the bottom represents the beef tallow. And the fat oxidation was higher on the MCT oil, but this effect was much greater after 27 days, as indicating by the much larger gap between these 2 lines. So MCT oil, because of the size of the fatty acids, and these are all saturated fatty acids, increases fat oxidation. Now, what I told you before suggests that it's not increasing the oxidation of fat instead of carbohydrate. It's increasing the oxidation of fat in addition to the carbohydrate in the meal. If that's the case, that means that total energy expenditure should be higher. And so again, day 1 is on the left, day 27 is on the right, and again, the line on the top is MCT oil. And once again, total energy expenditure is higher in both graphs, but you can much more easily detect this effect on day 27, as indicated by the much greater gap between the lines. Overall, MCT oil increased energy expenditure by 45 calories per day. Now, you might also say maybe this would affect food intake, because if your cells are getting more energy, then maybe they'll say, hey, I don't need any more energy, and you'll stop eating. So that was investigated in the context of a breakfast that contained several different fats. And then they said, all right, we'll feed the standardized breakfast. Then we'll say, we'll let the people ask for lunch when they want lunch. And we'll let the people eat whatever they want for lunch. And so what they were comparing here is, does consuming MCT oil for breakfast make you stay fuller for longer and take longer to request your lunch? And then at lunch, does it affect how much food you eat? And at breakfast, they compared a meal with a fat substitute to a breakfast with MCT oil, olive oil, which they called long-chain triglyceride unsaturated, and then lard, which they called long-chain triglyceride saturated. And as I mentioned in the beginning, lard is actually more unsaturated than saturated. But again, we see this common misconception. But then they said, okay, how long will it take you to ask for lunch? And I'm not showing you that data on the screen, but the subjects who ate the MCT oil breakfast took a lot longer to ask for lunch. What I am showing you on the screen is what did they eat at lunch, and you can see that out of all of the meals, actually the almost the highest was the fat substitute here, but out of all of the meals, the MCT oil at breakfast produced the lowest energy intake at lunch. And if you compare it to the olive oil group, that constituted 43 fewer kilocalories, or as we commonly say, calories with a big C, at lunch. So altogether, we can say that if you're burning 45 calories a day more energy, and if you're eating 45 calories a day less energy, then that amounts to about 150 calorie difference in total energy balance. And that can add up to a lot if your priority is weight loss. So this last study that I'm going to show you looked at weight loss. They compared MCT oil to olive oil, and that was with 49 overweight men and women randomized as to consume these oils as part of a weight loss program for 16 weeks. And that was in addition to nutritional advice, including reducing calories for the amounts shown for men and women. And you can see that MCT oil led to a greater loss in weight than olive oil did. And then finally, you can see the fat loss on the left and the lean mass on the right. And you can see that the MCT oil had a significant reduction in fat mass while the olive oil group did not. And they also had a small reduction in lean mass, but the decrease in fat mass was much larger, and so overall that would be considered an improvement in body composition. And I would note that it's quite typical to lose lean mass when you're trying to lose weight, and you can prevent that by either losing weight more slowly, eating more protein, or lifting weights. And they didn't investigate any of those things in this study. All right, now it's worth noting here that, as I said before, the value of this research, I think, is not so much to promote the use of MCT oil, but more to investigate the principle behind the effects on energy metabolism. And what I think we could say from this study, that there's probably a smaller but biologically significant effect of coconut oil here, and even of butter here, that would lead to much smaller effects on weight loss over time, that would be more difficult to detect in studies, but could be valuable to people whose priority is losing weight. And it may not only be beneficial for weight loss and fat loss, but it may also be beneficial for energy metabolism in the context of athletic performance. If your goal is to feel more energetic, or your goal is to improve your performance in a race, or a swim, or a weightlifting competition, or something like that, or if it's to feel more energetic while you're standing at the computer and doing some work that ordinarily makes you fall asleep, maybe, just maybe, the smaller fatty acids in butter and coconut oil would have a small but meaningful effect in those situations. Okay, butter, as I said before, contains about 5% of its fatty acids as these small saturated fatty acids. And most of that, in the context of butter, is the 4-carbon saturated fatty acid butyrate. Butyrate derives its name from the Greek word for butter, vutiro, and that's because the only meaningful source of butyrate in the diet is butter. And that's where it's found by far and away in its highest concentrations. Butyrate is also produced by our intestines, by our intestinal bacteria from dietary fiber that reaches them. And it seems that it's been so normal for humans to be exposed to high concentrations of butyrate throughout our evolutionary history that, in fact, our intestinal lining uses butyrate as its primary source of fuel. Now, butyrate has been shown in animal experiments to have some pretty valuable metabolic benefits, but it's also been shown in very small pilot studies in humans to be very beneficial for intestinal disorders. So, for example, 8 weeks of 4 grams per day oral butyrate in 13 patients with mild to moderate Crohn's disease caused 9 out of 13 to improve, and 7 of those experienced complete remission from the Crohn's disease. Can you get that from food? Yes, by eating approximately 1 stick of butter per day. In another study, butyrate enemas improved ulcerative colitis. This was a randomized crossover trial, which means that everyone got butyrate enema and a placebo enema, but they got them in random order. And this was in 10 patients who were unresponsive to or intolerant of the standard treatment. And the overall effect was to reduce their stool frequency from 5 per day to 2 per day, to stop blood discharge into the stool in 9 out of the 10 patients completely, and to lead to roughly 40% improvement in the signs of inflammation when looked using endoscopy or histology. There are also some interesting animal experiments on the effect of butyrate. And here this is data from a study in mice that were using the infamous lard-based research diet. I would say several very high-profile studies using this exact diet come out every year. And at any one time, we could say, like right now, I estimate that there are currently 50,000 mice, at least across the globe, who are consuming this exact diet. And they're all going to be in several high-profile studies in the next several years. Okay, so here they gave all of the mice this diet that is, it's not just high in fat, it's all refined food. There are lots of nasty things about it. And among those things, it doesn't have any natural plant foods that mice usually eat that have dietary fiber that would be converted to butyrate. And so it's very different from the natural diet of a mouse or a rat. In any case, they all got this obesogenic diet, but half the mice got extra butyrate. And you can see that in the mice that did not get butyrate, their fat mass just kept increasing over the 16 weeks. And starting out with lean mice, the percent body fat stayed stable when they were given butyrate, even though they were given this diet that always causes obesity in these animals. So giving them extra butyrate totally abolished the obesity that otherwise occurs in response to this diet. Not only that, but comparing them to the obese animals, the butyrate-fed animals had 25% lower blood cholesterol, 25% lower triglycerides, 50% lower fasting insulin, and a whopping 300% increase in insulin sensitivity, all consistent with abolishing the negative metabolic effects that come from obesity. One final thing that I'll note about saturated fatty acids is that they are not vulnerable to oxidation or oxidative damage in the way that polyunsaturated fatty acids are. This has less to do with the size of the molecule and is about whether it's saturated or unsaturated. But this is actually an advantage that saturated fats share with monounsaturated fats, rather than something that's unique to the saturated fats. So in a polyunsaturated fat, you have two double bonds, and the carbon that's in between those two double bonds is very unstable. Very easily can lose its hydrogen and expose itself to being attacked by oxygen, and that causes it to become a lipid peroxyl radical. That can then become a lipid peroxide by snagging a hydrogen from another fatty acid, in turn oxidizing it, leading to a chain reaction. And these lipid peroxides can easily fragment into dangerous small molecules such as malondialdehyde. I would say this process is somewhat analogous to breaking glass. Glasses are useful, they have a purpose, you smash it on the floor, it breaks into shards, and suddenly those shards can damage everything around it, and it's your priority to clean up that glass. Well, one of the roles of fat in the diet that is relevant at concentrations way beyond the structural roles of fats that we talked about earlier is that the more fat you have in the diet, the more fat-soluble nutrients from your food you absorb. And that's because fat helps solubilize those nutrients and make them easy to assimilate and stimulates all the fat-digesting machinery like bile acids and lipases and so on that help you break apart that food and absorb, say, vitamin A, vitamin K, vitamin E, vitamin D, and other fat-soluble nutrients in the diet. But some of those fat-soluble nutrients are easily damaged from oxidation. And so we could reasonably say maybe polyunsaturated fats in the diet are less effective than saturated and monounsaturated fats in the diet at helping you absorb fat-soluble nutrients. And there's one such study that shows this. Here they gave people a standard test meal that had a standardized amount of beta-carotene, and they said, okay, everything's the same, but some people are going to get safflower oil, which is mostly polyunsaturated. Some are going to get beef tallow, which is a mix of saturated and monounsaturated fats.
How does that affect your ability to A, absorb the carotene, and B, convert it into retinol, which is the physiologically essential form of vitamin A that we need in our bodies? And you can see the results here. The group that got beef tallow had 60% more absorption of beta-carotene, and although not shown on the screen, they had a very similar increase in the amount of beta-carotene that they were able to convert to retinol. There are some animal experiments that suggest that this isn't about saturated versus monounsaturated. It's about polyunsaturated on the one hand versus saturated and monounsaturated fats on the other hand. But if you look at traditional fats, that's exactly what we're finding in the traditional fats, like tallow and lard and butter, for example. You see a mix of saturated and monounsaturated fats, and you don't see really high concentrations of polyunsaturated fats until you get into the modern seed oils like soybean oil and canola oil and safflower oil and sunflower oil. Okay, so in conclusion, I'd like you all to join the Saturated Fat Club. Saturated Fat Club has 2 rules. First rule, don't fear eating saturated fat. Second rule, don't fear not eating saturated fat. Instead, cut out fear and be able to experiment freely to see what gives you the best health effects without fearing whether you're getting enough saturated fat or whether the saturated fat you are getting is going to kill you. Because there are a lot of strengths and limitations to all of these different fats. Butter is rich in vitamins and coconut oil isn't. Coconut oil has more immune boosting properties. Butter has butyrate. Coconut oil doesn't. We could go on and on about why they taste different, right? We could go on and on about the different reasons you may have for eating different things within the menu of traditional whole foods that we have available to us. And if you're making your decisions based on fear, you're not going to be able to listen to your body. And it's only after you cut out the fear of any type that you can actually listen to your body and see how you respond to your own diet. Any questions?
Hi, Chris. Thanks for this interesting talk. In my patients, I tend to worry about MCT oil versus coconut oil. MCT oil is derived from coconut oil. Is that process of deriving it from coconut oil safe, and are there chemicals used? Would it be, I guess if you want to concentrate the MCTs, you would want to go with straight MCT oil, but it's always for me this regular coconut oil versus the MCT oil, and how
that's a great question.
Making MCT oil, what is that about?
Yeah, that's a great question. I don't really know the answer to that. What I can tell you is that if your priority is to maximize body composition as quickly as possible, you're going to get a stronger effect from MCT oil. If your priority is consuming a more natural oil that you feel more confident is within the spectrum of traditional foods, I'd go with coconut oil.
So basically you're saying for a more targeted weight loss or something like that, MCT oil?
I don't know that you need to consume MCT oil to improve your body composition. I'm showing the MCT oil data because it shows proof of principle about the metabolic effects of those fatty acids. So I would say I can't think of a circumstance where the priority would be so high that I would say that person definitely needs to use MCT oil. But if someone asks me, I don't really care about natural, what am I going to get the effect from? I'm going to be honest and say everything would predict that you would get that effect more quickly from the MCT oil. Yeah.
And we don't know anything about the process of how it's extracted from the coconut oil?
I don't know that we don't know anything about the processing. I don't know anything about the processing that makes me confident enough to answer that. Yeah. There's no lauric acid in the MCT oil. Yeah.
I know the body processes the fats differently through the liver. Can you just comment briefly on the difference between some of the fats that you talked about?
Could you maybe elaborate a little?
I know that coconut oil doesn't always stimulate the liver in the same way that butter or a different saturated fat would.
What do you mean by stimulate the liver?
I know that, yeah, sometimes the body can more easily digest coconut oil because it doesn't require the same process to be absorbed.
Oh,
with
you're
the
talking about
bioproduction.
digestion? Mm-hmm. Oh. Yeah, so I don't know that I can really comment that much on butter versus coconut oil in that respect. I think there's a certain tolerance for medium chain fats in the diet, and beyond which you'll probably get diarrhea. And the diarrhea is probably from buildup of undigested fatty acids that occurs even at lower levels. So there's probably pretty early on you have less efficiency of digesting them, and eventually that increases to the point where it causes diarrhea. When you do digest the medium chain fats, they're transported very differently. So the medium chain fats go through the portal vein from the intestine directly to the liver. Most other fats get packaged into chylomicrons and are distributed through the lymph before they go anywhere else. And that, of course, is part of why the effects that I showed can even exist, because if they weren't going to the liver, they'd wind up getting stored in adipose tissue before it mattered whether they were getting into the mitochondria. So butter has a very small proportion of shorter fatty acids. So I would think that the digestive efficiency of butter would be higher. And of course, butter has butyrate, which acts very differently from the others. You're welcome.
I think my question may be a little similar, but more specifically, if an individual has a sluggish liver, introducing the saturated fats, do you suggest that they also eat foods that will ramp up their bile production?
By
So
sluggish
that they
liver,
can
do you
be
mean
more
sluggish bile
effectively
production?
cleansed through the liver? I'm not sure if I entirely
When you
organized
say
my
sluggish
question.
liver, you mean sluggish bile
You know, like
production?
fatty liver, people that have a lot of built up congestive oils in their body, maybe their bile production is compromised. You just go ahead and put them right on saturated fats, or do you suggest that they ramp up their bile?
I think those are. I think you're probably referring to a collection of different things that have totally different causes and effects that could have totally different implications for that.
That could
So
be.
if someone has fatty liver, the priority should be resolving the fatty liver. Chances are that person is overweight or obese. Chances are that person's insulin resistant and probably diabetic if they're not overweight or obese. And those are the fundamental causes of the fatty liver in those cases. If I were to try to fix the fatty liver beyond fixing the obesity and the insulin resistance, I would say dietary choline would probably be the biggest thing that could help. But I think for bile acid production, it may be helpful to include like bitters in the diet to stimulate that, but probably that person has a sluggish metabolism in general, because the main determinant of the liver's production of bile acids is thyroid hormone. And so in that case, I would want to be investigating the person's thyroid activity, because I would suspect that would be the primary issue there.
And these individuals that you're pertaining to, they can safely go on to these saturated fats and metabolize them and...
I don't think there's much of a difference in saturated fat and polyunsaturated fat with respect to fatty liver, except that saturated fats require a little bit more choline than polyunsaturated fats do. So in the context of a low choline diet, saturated fats could probably be harmful to the person with fatty liver because of that. But if you're optimizing the choline status, I don't think there's a significant issue that I would be concerned with there.
So you're saying saturated fats, choline, and possibly bitters? A combination?
Possibly what?
Bitters to ramp up your bile?
Yeah, I think so, but I think in the long term, the goal should be trying to see why the bile acid production is slow, and I would wager a guess that there would be a slow metabolic rate that's behind that.
Well, can the contributing factor be congestive oils in the body? People that are eating roasted nuts, potato chips, French fries on a regular basis, all these rancid, prepackaged foods.
I didn't understand the question.
Leading to the fatty liver. So then if you replace those bad oils with the good saturated fats combined with the choline and the bitters, is that the solution? Is that safe to do?
Yeah. Okay. So replacing rancid oils with non-rancid oils would probably be beneficial. I don't think replacing unsaturated fats with saturated fats is going to be very helpful or harmful if you're also optimizing the choline status of the diet.
Okay, thank you.
Thank you for your question. I think we're done. Thank you, everyone.